Welcome back to ECE 320A. We're in Unit 8. Homework number 8 is what you're working on, and exam number 3 will be coming at the end of this unit. And we're still working with Chapter 13 material, but that then means that we're working with convolution. And in today's video, what we want to talk about is developing an intuitive understanding of how we might arrive at or feel comfortable with these integral equations. And just be clear that I will be calling x of t minus lambda a flipped and slid waveform, or h of t minus lambda in the second equation as the flipped and slid waveform. It doesn't matter which of the functions inside the integrand are flipped and slid, but we can do the convolution integral based on whichever function is maybe easier or more helpful in our computation or in our analysis. So either of these two waveforms, they are equivalent, and you can use either one of those waveforms. In today's, we will actually derive it based on the top functional form, and that's where we're now looking at flipping and sliding the input, but we now are concentrating on this connection between the impulse response, h of lambda, with our excitation input, which is x of t, and in the convolution is a flipped and slid version of our original waveform x of t. Here is our system relationship. In the time domain, we have a block diagram description, but don't be misled. Don't be misled by this block diagram to think that, unlike what we were able to do in the frequency domain, we could find the Laplace transform of the output as the multiplication of the Laplace transform of our system's impulse response, which is the transfer function capital H of S, times the impulse or the Laplace transform of the input waveform capital X of S. That's no longer the case in the time domain. If we want to connect the time domain's impulse response with the time domain's input x of t, then if we want to combine those to produce the output, we have to do a convolution between the impulse response h of t and the input excitation x of t. So the convolution is between the system's impulse response h of t and the system's input to produce the system's output. And what we want to do now is develop this integral expression in an intuitive way. So here we are. Here's our input. And now suppose that we look at a specific input waveform, and let's say that it's now a weighted impulse. Now, if we were to look at the area underneath x sub 1 of t, it would integrate to an area of a sub 1. We're just weighting or scaling the input waveform, which is an impulse function, with a weighting of a value of a sub 1. Now that we have that, what does the output look like if we hit our system with an impulse? Granted, it's a weighted impulse, but what have we learned in previous videos? If we apply an impulse function to a system, what happens in the output? What is y sub 1 of t? Y sub 1 of t, if we apply an impulse function at the input, y sub 1 of t is just a scaled version. If we had a scaled impulse, it's now a scaled impulse response at the output. Or we could now say, if this is now t and the impulse looked something like that, here we would now have an a sub, well, whatever the impulse's waveform value is at time t equals 0, this is now y sub 1 of t. let's change that up a little bit. Suppose we delay the input, and now into our system, we don't start exciting our system until time tau sub 2. What now happens in the output? Well, again, our system, if it's a linear time invariant system, behaves no differently at 0 as it does at tau sub 2. So now y sub 2 of t is just a scaled impulse response, and its scaling is based on how much we had scaled the impulse function in the input to our system. This is now h of t minus, and it's now starting at time. That impulse response is starting at the same time that we started the input, which was at time tau sub 2. So that now we have something starting at tau sub 2, which is this weighted impulse response, which shouldn't go below 0 and to be consistent with my diagram above, but now we have, in terms of t, this is now y sub 2 of t. Let's look at another input. Suppose now that x sub 3 linearly combines or sums x sub 1 and x sub 2 to form a third input, a different input. This is now our third input. What happens to y sub 3? Well, I hope now that y sub 3, you can see, is just going to be the sum of the result from x sub 1's input and x sub 2's input, which we were calling y sub 1 and y sub 2. So now that's just going to be some a1 h of t plus an a sub 2 h of t minus tau sub 2. Scaled impulses. That's now y sub 3. Let's use that insight to figure out what might happen if we applied a slightly different waveform. Now these are not impulses, but they are sort of these stacked rectangles that gives us sort of this shaped pulse waveform that we want to apply to the input of our system, and we want to know what is the output y sub 4 of t to this new excitation input signal x sub 4 of t. What do we expect to have? Well, now we have no way of sort of thinking through this. If we could somehow approximate this green rectangle and the red rectangle and the blue rectangle with impulses, then we would have an idea. So let's just make that happen. We can. Now suppose that x sub 4 at time tau 1, let's just say that that now is the area of that green rectangle at time tau sub 1. And the width of these rectangles, we're just assuming for convenience, is a value of 1. So the amplitude of that pulse at time tau 1 is equal to the area of that, and we'll call that then x sub 4 of tau sub 1. Likewise, x sub 4 of tau sub 2 is the area of the red box or rectangle, and x sub 4 of tau sub 3 is the area of that third rectangle. And now we have these concatenated pulses of different amplitudes or different areas occurring at tau 1, tau 2, and tau sub 3. And we want to know what is y sub 4. Well, we can approximate that because we can now approximate these rectangles, these pulses, by impulses, where we weight those impulses with the value of the area of those rectangles. And we'll center those impulses at the appropriate times, tau 1, tau sub 2, and tau sub 3. Now you should be very comfortable with what y sub 4 tilde is. We just talked about what the output response looks like due to an impulse, a weighted impulse. Now we can immediately write down what y sub 4 of tilde is relative to these weighted impulses. Y sub 4 tilde is now x sub 4 of tau sub 1. That's the weighting on an impulse response that's going to start at tau sub 1. Likewise, x sub 4 of tau sub 2, that's the red, is going to now weight an impulse response that starts at tau sub 2. And finally, x sub 4 at time tau sub 3 is going to weight the impulse response that starts at time tau sub 3. Well, we can collapse this a little bit. We can say this is now just a sum over 3 terms, L equal 1, 2, and we could do this in general, but let's just say now up to capital N of x of tau sub L, h of t minus tau sub L. That's now y sub 4 tilde of t. Now, in the limit, as we enhance the accuracy, as we make these rectangles more and more narrow and chop up the time axis into finer and finer intervals of time, eventually we want to reach the limit where these time intervals, these tau 1, tau 2 distances are differentials. Then what's going to actually happen? Now instead of a sum, so let me write that down. If in the limit as we enhance the accuracy of our approximation, of, let's say, x sub 4 of t, we approximated it with x sub 4 of tilde. Now we want to make x sub 4 of tilde even better or closer to x sub 4 of t. Then the finite sum that I have here of capital N terms, the finite sum will turn into an integral. And now y sub 4 of t is now going to be this integral from, we could make this happen from minus infinity to infinity, of x sub 4 of tau, h of t minus tau, d tau. And that should look like the structure in this finite sum. Now we're just making that an infinite sum. The summation now becomes an integral, and we now are left with what we said we wanted to develop, which was this expression that we are now calling the convolution integral. And hopefully now you have a better feel for where that arises. Now we're simply scaling or weighting the impulse response at shifted values of time to produce what the actual output is in response to a particular given input waveform, which we're calling now x sub 4. That's now the intuitive idea behind the convolution integral. Now what we want to work on is evaluating that integral.